Hi everyone, this is Carlos with the Emacs Science Support Team, and today we are going to be looking at pyLIMA. pyLIMA is a microlensing modeling and simulation software. Right off the bat, we can click this download button, and that will take you to their GitHub page, where of course you can download their code. But also, if you scroll down, you will see that they have provided 5 examples for us, and they are all on Jupyter notebooks. We're going to go ahead and look at the first one, and the first one is titled How to Fit My Data. So that's what we're going to do. We're going to go ahead and fit some data. And before we get started, for those of you that are just here for fun, what gravitational microlensing is a phenomenon where light will bend around a massive object. So you can think back to how Einstein proved his theory of relativity. They waited for a solar eclipse to see if starlight from stars behind the sun would end up visible to us during that solar eclipse. So what you're seeing here is basically the same thing. You have this background star and you have this foreground star. As the two stars are coming into, as their separation angle is getting smaller and smaller, they pass through each other, and when that happens, the starlight from the background star will come, and the gravity of the foreground star will actually bend that light around it, creating this magnification effect, and making it look really, really bright. And that is what gravitational microlensing is. And we can actually use this phenomenon to find exoplanets, and I will show y'all how. So let's go ahead and fit some data. So first thing we're going to do is we're going to import all of our libraries. Easy peasy. Next thing we're going to do is we are going to create an event. So to create an event, you just give a variable, this event.event in open parentheses. You're going to name it. We'll name it Emac, and we will give it a right ascension and declination because we have to look at a patch in the sky, right? Now, the next part is we are going to define some telescopes to use. The telescopes we're going to use are OGL and LCOGT, and that being the Optical Gravitational Lensing Experiment and the Las Cumbres Observatory Global Telescope. We're going to give it a camera filter, so we're going to looking at the I-band, and we're going to upload some data, and this data is provided to us. So yeah, then we're just going to make sure that our event checks out. This insanity check is basically making sure that our data is getting put in the right format. So next part. Now we have to choose a model to use. So first thing we're going to do with our data is we're going to use the point source point lens model, PSPL, and this assumes that there's some separation between our two objects. Okay, so let's go ahead and use that module. Now what we are going to do is we're going to go ahead and use the damp least squares algorithm for our fit, otherwise known as this LM algorithm. I'm not even going to pretend like I can pronounce this because I for sure will butcher it. My apologies. So now let's print some plots. Really fun part about pyLIMA is that when you print a plot, it will open up a new tab for you to see your plot. So what's happening here is this plot is showing us our lens in this tiny little red dot, and then these arrows are indicating the direction of our point source. So right now, we have our two stars one is about to get in front of the other, and here we are looking at the flux our telescopes are receiving. So pretty uniform, and then when the event happens, you see this big giant spike in light, as you would expect, because the one in front is magnifying the light from the one in back. And then as the event is over, the light starts to dim, and then it goes back to normal. Scrolling over to the parameters, we have our T0, our time. We also have this mu0, mu0 being our minimum impact parameter. TE is our Einstein timescale. FS underscore OGL is the flux of the source for OGL, our telescope. G is the flux of the blend divided by the flux of the source. So the flux of the blend is, as the event is happening, there's going to be a little bit of blending of light. And then FS and G for LCOGT is the same. So going back to the notebook, that is our first model fit. As we can see, looks like there's some residuals around 80. we can zoom in with the tools that come with this bad boy. Yeah, that'll give us a really good idea of what we're seeing. So going back, let's see what the authors tell us. Again, they see some residuals at the peak, but they think that we can do a better job of fitting for this data. So the next thing we're going to try to do is use the differential evolution algorithm. Let's go ahead and run that. All you have to do is give it this DE, and it'll go ahead and run for you. Again, it will open up this new tab for you. And now zooming in on the peak, we see that there's almost not really much of a difference. As we predicted, the author is also not happy with the fit, so let's make it better. So now let's assume an FSPL. FSPL is science talk for finite source point lens. So now we're assuming that the separation angle is small, super tiny, finite, if you will. So you're going to use a little bit of different math. And if you guys want to look at the math, remember, you can always click on the ADS button so that you can look at the author's original paper, where they explain the math and break down the tool and all that good stuff. So let's try it. Let's do the same thing, but we'll assume that the separation angle is minuscule. So we'll run that. We'll use this again, and we will zoom in on the peak. Looks a lot cleaner now, and as you can see, our time is starting to get a little bit more precise. However, the authors still think that they can do a lot better, and I agree. So let's do it. Here we go. There's still some deviations around 80.1 days, right? Okay, so let's fix that. So now what we're going to do is we are going to try to clean up our data. So we are going to try to use some limb darkening techniques to really clean it up. So to do that, you will do this your event.telescopes. Remember, 0 and 1 refer to our two different telescopes, and .gamma. Gamma is a limb darkening coefficient. Yeah, so now we're going to use some limb darkening. We are going to plot, and again, it looks pretty much the same as before, although we are definitely starting to get more precise around those 80.1 days. We think that maybe the LM method is being confused by the limb darkening coefficients. So what we're going to do is we're going to feed it some initial guesses, run the model again, and wait for our plots to come up. So now we're getting really precise. And you will notice this extra parameter, this rho. So this is here because in FSPL, you are assuming that the separation is getting small and small. And in layman's terms, rho is the variable that tells us how close that separation is. So now let's zoom in on the peak again. Whoops. We'll zoom in. Now we're getting really clean. So it's looking good now. And to confirm, we will do the same thing, but with the DE method. This plot opens up. We can zoom in on our peak. Now we're really closing in. This is awesome. And just to triple check that everything is good, we are going to do the same fit, but now within MC. And let's wait and see what our corner plot looks like. So this is what opens up. We'll zoom in on our peak one more time. This looks super clean now. All of our parameters have been refined, and we can scroll down to our corner plot, and wow, that is a good looking MC. So that is pyLIMA. It is a very useful tool. It's really cool. And then as a bonus, if you have data and you think your data might have an exoplanet, what you want to be looking for is this peak. So here, as our event is occurring, right here, we have optimal magnification. So we're getting tons of photons come into our telescope. As the event is finishing, the planet also becomes a lens, and you get an additional spike because that little spike will give you a bunch of photons come into your telescope. So if you guys are playing with pyLIMA and you have some data and you put it in, and you happen to get one of these bad boys, you might have an exoplanet on your hands. I hope you guys enjoyed today's tutorial. If you guys have any questions, comments, or concerns, you can always comment down below or DM us on Twitter at ExoPlanetModels. Thank you. Peace.